Let's say we throw a hot cup of coffee into a black hole. The black hole changes its mass to some degree based on the cup of coffee falling into the black hole. But the question remains, as an observer on the outside of the black hole, what happens to that cup of coffee when it enters the black hole? We could go further and say, what if you were blindfolded and handed this hot cup of coffee to throw into the black hole? How could you know that what you threw in was a cup filled with coffee and hot?
These attributes that make up the hot cup of coffee we can refer to as information. Our project seeks to evaluate the claim, is information lost when an object enters a black hole? Or in other words, can we salvage what went into a black hole based on how the black hole reacts with the object being thrown in? This is the black hole information loss paradox.
This may seem like an arbitrary philosophical question, but we see this as a necessary step in advancing the field of physics. Evaporating black holes stand at the intersection of many fundamental fields of physics: thermodynamics, statistical mechanics, quantum mechanics, and general relativity. In particular, no one has yet come up with a way of reconciling quantum mechanics and general relativity. So studying evaporating black holes is one way to discover how this might be accomplished.
In more concrete terms, the black hole information loss paradox is understood by the following debate between Stephen Hawking and Don Page regarding the entropy of an evaporating black hole. Here, entropy is a unit of measurement to describe the complexity of a system, and depending on the field of physics you are in, it manifests in different forms. In our case, information is analogous to the entropy of the system, in that the more complex a system, the less information we have about the system.
Hawking's prediction uses entanglement entropy, an entropy found in the field of quantum mechanics that allows us to determine the mixedness of the state of the black hole with that radiation. States are a way quantum mechanics describes the composition of a physical system, and by measuring their mixedness, we can tell to what degree the two physical systems are interacting with one another. Hawking finds that in quantum field theory, the entropy of a black hole increases until relative max, when the black hole has reached singularity or when it fully evaporates.
In contrast with Hawking, Page incorporates argument from statistical mechanics that prove contrary to the predictions of quantum field theory. His argument claims that statistical mechanical entropy proves the evaporation of a black hole is measured twofold, one of the black hole and the other of the radiation the black hole produces. Because the black hole and the radiation it gives off are two different quantum states, we know that as the black hole evaporates, there exist two unmixed states, A, a pure black hole state, and B, a pure radiation state. This is because physically, a black hole begins its existence without having emitted radiation and dies leaving behind only radiation. For this reason, the entropy must return to zero rather than reaching a max, subsequently proving that information is never lost.
These two contradicting theories are the main iteration of the black hole information loss paradox, and the importance of our work in resolving this debate is evaluating the validity of two long-standing theories, quantum mechanics and statistical mechanics, to see how they may be impacted by the physical characteristics of a black hole.
In order to resolve this debate, our project investigates a mathematical theory called the entanglement wedge reconstruction, which sides with Page's argument in the debate.
The entanglement wedge hypothesis claims that whenever we carve out a chunk of the space and time of a certain system, in our case a black hole, we can slice that time into a way where we reduce the entanglement entropy of a system. In this way, we find both that A, the entropy of the system matches Page's prediction, and B, that we are able to represent the interior of the black hole even from the perspective outside of the black hole's event horizon.
The importance of this theory within our research is that it provides a mathematical argument for the previous graph that was only hypothesized, not yet proven by Page. We hope that within our research, we not only resolve a popular debate surrounding the physical nature of black holes, but also use what we learn to expand the disciplines used to understand the physical systems of our universe.